I'll get started with the housekeeping, which you probably have all heard repeatedly, but please silence your phones. Photography of ABRF meeting sessions is permitted, subject to speakers' requests not to capture pre-publication info. Is everything here okay to take photos of? Excellent, thank you. Recordings of the program will be available on the meeting website following the annual meeting. Our social media policy is that everything can be shared unless the speaker asks you not to share it, so please be mindful if they do say that. We're going to try to hold questions to the end. If something's really burning and you can't wait, I'm sure our speakers would be willing to entertain that. If you haven't downloaded the ABRF meeting app at this point, give it a try. There's some good stuff in there. And please keep an eye out for the survey after our meeting, because there's a lot of good content we get from that to be able to inform what we do in future years. So with that, we'll get started. Thank you for coming to the 3D printing. It said in-core facilities before, but it's just 3D printing core facilities. We're going to hopefully have a good conversation about 3D printing capabilities and a few other things. My name is Andrew Vinard. I'm the Director for Research Infrastructure Support at Tufts University in the Vice Provost Office. Taking the lead a few of my peers. Nope, that's on here. Little background on Tufts.
Not working?
Not yet, it was just a minute ago.
You restart your presentation, sorry.
No. There we go. Thank you. Tufts is a 4-campus Boston area institution with about 13,000 students, 1,500 employees, faculty members rather, and about $273 million in research funding last year. My specific responsibility is research infrastructure. We have about 374,000 square feet of lab space, thousands of pieces of equipment from individual benchtop things all the way up to specialized instrumentation. It says more than 30 core facilities. I'm going to change that in the near future, and based on conversations here, it kind of depends on how you classify a core facility, but quite a few operations, the majority which are run by the departments and centers, a couple that report in centrally, and about 40,000 square foot of animal care space. My specific role at the institution is to work on the research infrastructure, make sure people know what we have, know why it's important, how to access it, make sure what we do have is functioning and sustainable, and then moving forward, working with the cores, those that are in the departments and centers, making sure they have the resources they need to be successful and sustainable. So everything from business plans to helping them with S10 grants to finding out best practices and everything from HR to everything we've talked about this trip. So we're here to talk about 3D printing, and why am I talking about 3D printing? The short answer is because I can't say no. But more importantly, it's because ABRF has done a really concerted effort in the last couple of years to expand beyond the bio. So in our name, we have biomolecular, but we are much more than that. Regardless of what modality you're working in, what kind of facility you're operating, there's a lot here at the meeting that you can glean, and us having folks that are also in non-biomolecular cores helps us learn the best practices you have in those other types of facilities. So a lot of colleagues and a lot of friends around the country and world have a big responsibility for materials cores, and we kind of almost excluded them for a while. So again, the push to bring folks that are in other areas is really important to me, and we've seen a really big push and response from the folks that are coming from elsewhere. Especially if they are part of other societies, it's almost like we're working in parallel and not realizing we exist. So just to belabor the point that having folks here in other areas helps us all be stronger. We're going to have 2 speakers today. We're going to have Nick Fiorella from Tufts University Comparative Medicine Services, and he's going to talk a little bit about his journey in 3D printing, how it's being used to support a broad range of needs, and more importantly, one of those other non-traditional ABRF categories of cores, how it's being used to support animal services and care. Then we're going to hear from Dave Follette from UMass Amherst Institute for Applied Life Sciences, a little bit about how they operate up there and some focus on the importance of people. And all range of people from design engineers to students, and hopefully we'll have a good chance to get some good dialogue, good questions and answers, and hopefully everybody walks away with a good understanding of the different 3D printing models for cores that are out there and capabilities, and something that I think shouldn't be just with 3D printing but all cores, understanding the importance of expertise versus just technologies. So with that, I'll pass it over to Nick.
Hello everyone, I'm Nick Fiorella. Like Andrew said, I'm also at Tufts University. My position is Special Animal Initiative Strategist. It was a whole bunch of words we jumbled together because I just found myself getting into new and bigger projects at a wide range. And one of these things I took on was 3D printing. So 3D printing is changing the way we approach problem solving and research. It offers custom solutions that were once expensive or impossible. But what if your institution doesn't have a dedicated 3D printing core? That's where this homegrown approach can come in, and we'll show you how to do that. So whether you're completely new to 3D printing here today, or you're looking for ways to expand it in your own lab, we'll give you some actionable steps to take away. Before diving into the hands-on aspect portion of it, let's take a look at 3D printing and how fast it's actually growing. So 3D printing has rapidly grown across many industries, but the most exciting area is the one where it makes the most impact, I think, is biomedical research. Particularly in lab animal medicine, it allows researchers to develop custom solutions that would have previously been too expensive or difficult to make or buy. This graph shows the rise of 3D printing mentions in PubMed over the years. As you can see, the exponential growth. It looks pretty linear, but the first mention was back in 1960s, and then from 1960 to about 2010, there's only a couple dozen publications printed every year. So draw that graph out. It has a pretty rapid rise over the years. Researchers are increasingly recognizing the value of 3D printing in preclinical services, surgical models, imaging tools, and even enrichment devices for lab animals. Despite the surge in interest, not every institution has a dedicated 3D printing core, but that doesn't mean you can't leverage this technology. In the next few slides, I'll show you how we've taken a homegrown approach to this, using a small 3D printer to solve real-world problems in our research facility. So, 3D printing on a budget. A common misconception about 3D printing is it requires very expensive equipment or advanced engineering skills. In reality, you can start with minimal costs and still produce high quality, useful prints in research applications. The first step is designing or finding a model. There's a lot of free beginner software like Tinkercad, Fusion 360, and OpenSCAD. It makes it easy to start from scratch and build something unique. I'll show you more on Tinkercad later. That's the platform I use. But you don't always need to design from scratch. There's a whole bunch of open source areas that you have, like pre-made models that you can use as is or modified to fit it to your needs. That definitely saves some time and effort. So if you need a custom holder for an imager, you can tweak the existing design rather than starting from scratch. And then, as always, a lot of my stuff I taught myself, and YouTube is your best friend. Someone's had that problem before you, and they probably made about 5 YouTube videos. So even if you've never talked to an engineer or tried engineering out for yourself, go on YouTube, and then you can become a semi-professional. So one of the first open sources is this website called Thingiverse. It's all free and offers over 2.5 million models. It ranges everything from trinkets that we have up here to just random little household appliances. Here's just a couple that, I get requests from people in my office all the time because just these little things are useful. You have some random piece of lab equipment that the cord always gets in the way when you're trying to do it. That's cents on the dollar than ordering something on Amazon for $5. And all the way at the end, that is a pipette. It's not volumetric, it's just a straw, so it's more for fun. Don't actually try using any of that. So the other open source one is going to be the NIH 3D Print Exchange. This is actually the first government website that was created for 3D printing. It specializes in scientific and medical 3D models. Unlike open source platforms like the prior one, Thingiverse, this database is specifically designed for biomedical and laboratory applications with all validated 3D models. One of the biggest advantages of this platform is that researchers can not only download, but they can upload their own 3D models, adding to their growing library of validated designs. By sharing your model, you get a couple benefits. It helps standardize research tools, so if someone's trying to replicate your study, they don't have to try making that same object. They can just download what you made. Help collaborate with other scientists, increase in visibility. You know, you have some great invention, you want to get it out. You don't really care about making money. You just want to help science grow. It's a great place to do it. I think the coolest benefit of this library that NIH has is every time you upload a device, it will create a unique DOI. So in any of your white paper studies, you will be able to reference that in your citations. So like this first one right here, this is an axolotl, and they're printed in different sizes, and it basically just holds the axolotl while they can collect the sperm for cryopreservation. Over here is just a simple clip. This is a frog tank. Pretty often these plastics just break down over time, the lid, and they get flimsy, and it's just a super inconvenience. So this guy, I don't know who designed this one, but somebody saw the problem and made a simple solution and put it out for everyone. Another one over here is a surgical setup for a mouse. This 3D printed part is the blue part. It's the nose cone for the anesthesia, so whether they had broke it or needed a better fitting one, they were able to design it and print it out to fit it into their own setup. So a little about the printers that I use. Once you have your design, you need a printer to fit your budget. Fortunately, there are several low-cost printers out there. I originally started buying with my own personal money, this one on the end, Ender 3, and then you just quickly realize you can do a lot more with a little bit more money. So that one was about $200 on Amazon and moved over to $400. And this one's pretty cool. You know, you get a little bit more temperature range, which means you can change your materials, your plastics. And then finally I said, why am I spending my money? I'll have Tufts buy me one. And this Dremel right here is about like $2,500. It just, same thing, it has more broad range of temperatures, so more stuff you can do. Best materials for research, PLA for general use and PETG for durability. TPU is another good one for flexible objects. Things to look for is good heated bed, good community support, and ease of maintenance. So kind of like that same aspect of going on YouTube. You know, if you buy a real obscure one on Amazon, they may not have the best support, or someone had that problem. But name brand like Dremel had a 10-year warranty and a whole bunch of people that use it and know all its problems and how to fix them. So going into some of the things that I've used it so far, right off the bat, so one of the other hats I wear is I manage the zebrafish facility. When I initially took it over, we had about 1,500 tanks, and when I was taught the beginning stages, they said, we're going to take this little straw and feed 1,500 tanks. And I did that for about 2 days, and I said, wow, this is absolutely ridiculous and a waste of my time. So what I did was started off with a couple different prototypes. Initially, I just took a simple tube and ran a spring with a long screw through it, and that allowed me to actually cut my time down significantly. But it's just not the easiest to clean and all that stuff, so basically I took it to the drawing board and made it on a computer, and this is basically the final design that I made, printed it out, and now I'm able to feed the fish in about 10 minutes now compared to like an hour and a half. So this one right here is PETG, so it's food safe, and we use Clydox to clean that.
Is that on your
No. Yeah, there's a couple other zebrafish feeders that they made that I tried. I printed out one time and it wasn't great. So another problem that we had was this middle picture right here. This is the isoflurane chamber for mice. At one point we had an investigator, I don't know what happened, but the mice must have been left unattended or not, because it has a lid and then it has another security lid that you could see back here that's flipped on top. And this right here is the little vacuum port to suck up and scavenge all the excess gas. And one of the investigators wasn't paying attention, and then a mouse got pulled up into that vacuum tube. So one of the vets came to me and said, "What can we do?" And this was just actually a pretty easy one to do. I had designed this little cap right here and just capped it off. So not blocking any of the vacuum suction, but still stopping mice. So going back to Tinkercad, Tinkercad is really cool. Think of it as like building blocks. It's actually how they teach kids early 3D modeling, but it's actually very simple to manipulate yourself. So when we look at the object over here, basically all I did was measure the inner diameter of that hole, and then basically just start with shapes. So, you know, 1 circle, 2 circle. In your whole library, they have a whole bunch of other shapes, but it's just building blocks. You know, just change what kind of shape you want. So here's just a outline of it. This grayed out part, that just means it's a hole. So then you start just grouping your objects together until eventually you get to this product. So that was a fairly easy one. The fish feeder, that's like probably a couple hundred different shapes put together. There's probably easier ways once you get into really good 3D design, but this is my basic approach. Another challenge, we had some tree shrews come into the facility. The investigator spent a ridiculous thousands and thousands of dollars on these special made cages just for the tree shrews, but the doors would never stay closed. If the animals weren't escaping, the animals weren't manipulating the caging, it was just they made really bad latches. So with 5 cents and a couple different shapes, we just made a C-clip that closes that. Some other things that I have around the facility, a lot of investigators get really nervous about handling mice. They've never handled a mouse before. So that hesitation of picking up the mouse first time, that's when the danger of them getting bit by mouses. So, you know, here's a little scruff guard that you can just put over the mouse. It kind of isolates them, and you can just pull their skin through the back, all humane, and then you can do IP or any other injections that you need. This next one is in my fish lab. I just had bottles everywhere and tubes everywhere. You can just print hangers. So instead of going on Amazon, spending more money, and trying to figure out what even to Google, you can make it yourself. Over here is a cool aspect that I really like about 3D printing is really fast prototyping. So we have a cannulated pig model that we have at Tufts. And we are always working on how to make these ports better. So basically I'm able to design this early stage one go to the vets and surgeon, and they provide their feedback, and then every model we just keep on updating. These plastics are more prototypes. Once we get the model that we actually like, we'll end up eventually sending out to another facility that has a lot more expensive printing that can do biocompatible plastics. So some final thoughts and concerns. While 3D printing opens up exciting possibilities for research and lab animal medicine, it is important to recognize the potential risks. Not everything coming off a 3D printer is automatically safe in the research setting, especially working with animals. One of the biggest concerns is material choice. So chemical leaching is definitely a huge concern. This is where some material may release trace elements over time. This is critical if the printed object is in prolonged contact with food, water, or just animals in general. So not all 3D printing filaments are created equal. Some contain harmful additives and release toxic compounds when heated. So a couple, for example, PLA, generally safe, biodegradable, very commonly used. However, it's not very durable or heat resistant. ABS is another popular one. Strong, but it does release harmful fumes when it's printing. PETG is the one I commonly use. It's a great alternative, durable and food safe, making it a good choice for lab environments. Always check the safety data sheets. A lot of these companies will have their safety data sheet, but they don't do routine testing in their plastics. So you can't guarantee the purity of the plastic that you're getting. Unlike traditional manufactured lab equipment, 3D printed objects have layer lines and microscopic pores that can trap bacteria, making it difficult to sterilize. This is especially concerning in environments where sterility is critical and for surgical and behavioral studies. So some mitigation techniques. Certain plastics, you can get acetone, put it in a container with a little acetone vapor, and it will smooth it out. So this little fish castle right here was basically the outside layer of the plastic gets melted and it really smooths it out. Another option is encapsulation. So this is a fish hide that I made. And then a trick I actually learned from the people at Tanked down in Vegas. They do all the fish tanks. Just throw aquarium safe epoxy on it and you just encapsulate the whole entire object. So the other problem is 3D printed objects are strong enough for long-term use, say, but prints do fail the layer adhesion, pore infill, and proper design. Examples of that, so you have an animal restrainer or surgical guides breaking mid-procedure, that's definitely a hazard. Cage accessory snapping, creating injury risks to the animals. And finally, regulatory and compliance issues. Depending on your institution, there may be compliance concerns using 3D printed materials in your research lab with animals. So IACUC approval is always suggested. If using 3D printed devices in animal studies, it may need to be reviewed for safety, as most of these common plastics aren't biocompatible. And then record keeping too, along with that. If using 3D printed to create experimental tools, keeping clear documentation on material choice, print settings, sterilization methods is essential. So in closing, my closing thought is 3D printing is a powerful tool, but like any tool, it needs to be used responsibly. Choosing the right materials and understanding structural limitations, ensuring proper sterilization are key to integrating 3D printing into lab animal medicine. If you are aware of the risks and take heed, we continue to innovate without compromising research integrity or animal welfare.
All right, good afternoon, thank you for having me. Andrew, thank you for putting this panel together. It's nice to be here. This is my first ABRF, and I'm glad to bring a topic that's a little bit different than genomics, because all of that stuff out there is not what I do. I do 3D printing, specifically additive manufacturing. So my name is Dave Follette. I am from UMass Amherst, and our core facility is called the Advanced Digital Design and Fabrication Core Facility, which is a mouthful. So we have shortened it to AdFab, which has the idea of additive and fabrication in it. We've been going for about 6 or 7 years now. We were fortunate to get a lot of equipment up front as part of a large grant from the state. So instead of having to build it from the ground up, it was more like build it and they will come. So I came in and we had lots of equipment, and the question was kind of, what do we do with this? How do people know what to do? How do we make the best use of this wide array of equipment that we have, and to make it useful for the university and beyond? So when we started, a lot of our marketing was kind of a list like this. We have all these machines, they have all these numbers, the P110, the 252P, the Objet 350, and that's great. We have a lot of nice numbers, but this is pretty boring. This doesn't tell you what they can do. This doesn't talk about solutions. So what I found is more interesting and maybe more effective over the last few years is to talk about what we can do for you. You don't care as a user if I use the Markforged Onyx 1 instead of the Profolytics P285D. That doesn't matter to you. What matters to you is you got the part that solves your problem. And being an engineer in sort of a science, I'm in the life science building, most people aren't engineers. They're not here to design parts. They're here to get research done, to do experiments. And so we've been trying to find a way to work together and not just use the 3D printers, but apply some engineering design expertise to really come up with solutions. So to start, why do we use 3D printing at all? I think Nick's done a great job of showing lots of examples. Some of the things that I think about come from this example. So I also am the technical advisor for the student formula team. So this is an undergraduate team that builds a race car over the course of a year and competes in Detroit at the end of the year. It's pretty fun. I would highly recommend joining if you are in that position. And so we need to print things like intakes. Oh, this is fun. We have intakes for the engine, and you might wonder why we printed them in PLA, which is a low melting temperature plastic. The answer is it's fine if it's on the intake side. Exhaust side, less good. But it requires someone who understands what the melting points of different materials are. The students will come and say, I need this in metal. I say, well, okay, metal's very expensive to print. Is this really what you want to do? What are we doing? Oh, air intake. Okay, room temperature. All right, PLA is fine. You're going to change the design 5 times anyway, so I'm going to print it in a cheap material quickly for you. So that's worked great. By the way, if you want to talk details about all those printers and ask about different types of nylon powders and titanium versus stainless steel, all those things, please ask questions in the end. I'm happy to talk for 2 hours about the nitty-gritty details of all the different kinds of printing. But still talking about kind of solutions, why do we 3D print at all? It's fast. It can be cheaper in a lot of situations. A lot of manufactured goods are cheap because they're in high volume. If you're doing low volume using, say, machining or any kind of metal forming, is actually very expensive for small volumes. And since our volume is usually 1, with complex shapes and things, being able to get rid of the setup fees, get rid of the shipping, you can actually be quite price competitive even on these complicated custom designs. And as an engineer, and I mean, you've all seen things on the screen in 3D, that's great. You can rotate them all day long. But there's something about holding it in your hand, putting it together, and you just get such a different experience and understanding of the part or the thing. We've printed quite a few models for people that, they've looked at proteins on the screen to death. They've put them together in different ways, but just having it in your hands makes such a difference. The other thing that I like about it is because it's fast, you can quickly iterate. There was a time when I would carefully check my models over and over again, but I don't even do that anymore. I just print and then go right to there and then learn from the design right there. You could look up the tolerance for a screw, how big does the hole need to be to fit, or I can print 3 sizes and see which one fits. So I've really gone to this sort of experimental mode, which is a lot more fun as an engineer, I think. So this was a project we had for a faculty member who's doing UV sterilization on a sheet of glass. So she's got a sheet of glass in the center, and came with this problem. It was, I have these LED lights, they get really hot. I need them to point at the edge of the UV glass. How can I hold all these things in place and cool them? And I just want to point LEDs, can you make this work for me? Yes, we can make that work for you. But it requires a lot of steps. You have to think about, how am I going to cool these LEDs? Oh, well, what's similar to an LED? How about a CPU cooler? So these are chip coolers from clearly a gaming CPU. There's lots of flashing LED lights in different colors, which is great. But how do you incorporate all of those, hold the LED in the right place, and keep them cool? So we came up with this design. And then the question is, how do you print it? Well, is that a question for the customer? Do I ask them which one of these they want? Sometimes, but usually it comes down to what their requirements are. So we have lots of options, and each of these is good in a certain situation. We can go through each one and the pros and cons, but for this application, it was best to have something quick, something that could hold it in place. It wasn't going to be underwater. It wasn't going to be sterilized. It wasn't going to get warm. So really the cheapest option in PLA was going to work great. I like this printer a lot. It's a Prusa XL, goes for about $2,000, so it's not exactly your entry-level printer, but for a core facility, that's kind of entry-level for us. But it does a great job with PLA, very reliable. We like it a lot, so that solved their problem nicely. The other solutions I'm going to talk about are not necessarily from faculty, but from a course that we ran. So there was a program called the Biotechnology, BTP, Biotech Training Program, run by the NIH. So they had a grant to do a lot of training for graduate students, and I was approached by the person who runs that program and said, can we incorporate 3D printing? And my goal is often to kind of evangelize 3D printing within the community. And what I've seen is there are a lot of biologists with lots of great ideas in the lab, lots of things they want to fix, but they're missing the design component. So they have an idea, there's a 3D printer to the part, but somehow you have to design the part, get it into the computer, make a 3D model. So Thingiverse and NIH are a great source for models that someone else has done, which can be good if you have the exact same problem. Oftentimes they need little tweaks, and more often you kind of want your own custom thing that's exactly what you need. Unfortunately, that requires someone who knows design, doesn't have to be an engineer, but a really good fit for that has been undergrad mechanical engineers who have just learned CAD, are eager to apply it to design things, but there just aren't really enough problems for them to dig their teeth into. So the way I set this class up is to have grad students come in, tell me about a problem in your lab that we can solve with a physical part. I pair you with one of my student intern mechanical engineers. They work together to do a design, we print it, they test it in their lab, we do an iteration, and we print again. So it's really fun to see these ideas kind of come to life and give sort of these younger engineers a chance to work on these projects, which I guess I could do, but usually a little bit too simple for me to work on. So it's a nice fit there. We did a lot of centrifuge tube holders. I didn't know how many tube holders biology needs, but it's like you're holding tubes all the time. In their situation, I think the centrifuge, I think they could fit, five of their tiny tubes in kind of the giant holes. And it was a bottleneck because this would run overnight, and that meant you could only run so many samples overnight, and all the students wanted to use it, and you'd be waiting to get time on the centrifuge. What if we had something that could hold lots of tiny samples instead of just a couple big ones? So we designed a couple iterations on that. And really a pretty easy design and print part once you know what to do. And we even added some custom labeling so that it was labeled what types of tubes are going in each one. So engineering-wise, not that hard, but for their workflow, really helpful. Another one was interesting in that someone else in the lab had this part already, but it was so popular that other people couldn't use it. So they want a copy of it. They had forgotten where they found it. So we actually reverse engineered this one. It helps you mix stuff from 2 different syringes. Not particularly hard to reverse engineer, but we were able to also write their name on it so different labs wouldn't take it from them. And once you have a 3D printed model, you can actually make as many as you want, which is pretty convenient. Now that I think about it, we can imagine uploading this to a database like Thingiverse or NIH, a little bit outside of my scope, but something we can think about if that's important enough to these students. So it was a reverse engineering component, and then we chose a different material for this one, which was a nylon 11, printed using an SLS process, because that has much better chemical resistance, much easier to clean, can handle high temperatures. Costs more, but it's a small part, and needed to be kind of watertight and have chemical resistance. So we made that decision. This one was a visualization. So it's a hydrogel network structure. You can look at it on the screen, you can spin it around. I can't remember exactly if it was this one or a different one we did, but a student described it after they had it, that they would go to the whiteboard with their PI and they would draw the 3D structure on the board and they would talk about it, and they couldn't quite communicate what they wanted, but once they had the 3D model, they could turn them in the right way, and the PI and them could both understand what the 3D structure was that they were trying to come up with. So sometimes it really takes having something in 3D. You can't quite communicate it with 2D and with whiteboards and computer screens. So another one we did, so little proteins, scale, much larger than you would see in real life. What was good about this one is this is actually tricky to print on most 3D printers. Your sort of consumer grade ones, this is a powder-based 3D printer. It has lasers that melt the powder on different layers, so it's actually held in powder while it prints, so you can print these very fine details. Very easy for us to print, very hard to do kind of the design for that. Interestingly, we could take I don't remember where we got the data, but there are 3D models of these proteins, and then we could do a nice model of those. This one I like a lot too. A lot of these have an interesting backstory. I mean, I don't pretend to know exactly what this experiment is, what they're experimenting on, or what they're doing, but I do know that before this, they would stack up books so their sample is at the right height. So that's great. It's not super repeatable when the books like disappear and you're like, oh, which book did I use? I need the same height as last time. So it's not hard for us to print a box for this. And once we have a box with the same size cylinder there to hold their sample, you get the same height every time. You're not looking for the same textbook so you get the same results. And it's much more repeatable, much more calm for the student, and it's good to have a setup that's consistent. So this is also one of those that helps with repetitive motions. This student came in and had a problem with, they were getting tired, their hands and their feet were tired because they would put something in this flask and then they would have to hold it in warm or cool water for 15 minutes while it warmed or cooled, and they would get tired. They didn't have anything that could hold this shape of flask exactly in a tub of water at just the right temperature. So it took a couple iterations to build kind of this canoe thing with outriggers and flotation devices, but it is hollow inside. It has air. It has little rubber bands that allow it to grab around the flask. So this is a more complicated design, but the quote is great. How could I ever forget about one of my favorite courses? My lab still uses the floaty designed in the course to this day. So that was great that we could help him out. And pretty much every student left with something that made their lab a little bit easier to use. Might have been a total of 2 or 3 hours spent with an engineer to design the part, and then a couple iterations printing. And so I think my takeaway is that we have a core that has lots of great 3D printing capabilities. You can print metal, you can print polymers, you can print squishy things, you can print them together, but just those printers alone don't solve the problem. What you need is a printed solution, and so that requires some kind of designer or some kind of engineer. That can be a graduate student or a PI, but those skills often don't overlap with having a PhD in biology. And oftentimes that's not exactly how they want to spend their time. It can be the core facility director who does that design. I do it sometimes. I try to take on the more complicated things and share the easier things for my students. And I have had lots of great undergraduate engineering students who not only have sufficient skills to do these things, but I think get really good customer engagement kind of experience. I put them right in with the grad student, and it's up to them to figure out the solution to the problem. There's certainly mentoring that goes on, and I'm there to help if they need it. But I really like it as an opportunity to interface with the customer, understand their needs, and provide a solution for them. So if you want to get into this, you don't have to spend the $3 million that we did to get fancy 3D printers to do lots of stuff. You can easily start at the $500 or $1,000 range and really get a lot out of that. We can talk more about what you get when you start to spend 6 or 7 figures on a printer, you start to get different things, but that's not necessary. But I think it's important to remember that you not only need the printer, so a few thousand to start, but a lot of people forget there's a person, say a core facility director with expertise that is required, or some kind of designer, engineer to really facilitate this process. The printers by themselves don't tend to just spit out solutions as much as we would like. Printing materials themselves really can be pretty cheap. PLA can be had for $10 or $20 a spool, and really fancy materials can be up to $200-300 per kilogram. You can get some really fancy polymers that do nice things. Those have specialized applications. So sometimes you need that, sometimes you don't. Some of the skill is knowing when you need those or not. So to wrap up, the benefits that I think everyone gets, more accurate and reliable lab setups. I think that's often, well, I won't say it's often overlooked, but I see a lot of Velcro, I see a lot of duct tape, I see a lot of zip ties, and I think, if we had something a little more secure, I think this would be a little bit more repeatable. And we've had a lot of researchers who have these ideas and they do something, and it's not their area of expertise to design parts and 3D print them. They're doing science, and that's what they should do. I'm doing engineering. I will help you engineering, you do science, and it seems to have worked well in a lot of situations. And I really like the one where we're making it easier for the people doing the work. So the grad students who are doing the experiments, less tired, less bored, makes you more productive, and I think you do a better job. So if I can make someone's life better at the end of the day, that makes me feel good too. That's all I have. I actually brought, I'll talk about this a little bit. This is my giveaway for today. There aren't that many people here, so you might have enough for everybody. This is something you find on Thingiverse. It's called a Flexi Dragon. It is printed in multiple pieces that, it was printed as one piece and they all are attached and they move. It's printed in a 3-color filament, which is pretty fun. I will say I don't like the idea of 3D printing just being about giveaways and toys, but I love these so much and I think they're fun. And if you go home and say, 3D printing's great, look at this everybody, that was my goal. So after the talk, if you want to come up, we have some up here and you're welcome to get them. So thank you very much.
Thank you, Dave. Thank you, Nick. If folks have questions, and actually, let's make it interesting. If you want a dragon, how about you come up and ask a question? And please do it to the microphone.
Woo, dragon. Hi, Matt Kaplan, University of Arizona, Tucson. I run a high-throughput biology core, so I 3D print custom stuff for my robots because Beckman Coulter costs a fortune for a tiny little thing that I can make in an hour. But I also have gotten into the realm of like custom centrifuge buckets, and I'm always worried they're gonna fail. and you're the engineer and I'm a biologist, that PhD biologist who you said shouldn't probably be doing this, but I've been doing it for a dozen years. Do you do any, like I just assume, hey, you're spinning cells, don't spin them that hard, and I'm making it with like a lot of infill, and then by the way, I clear coat with Rust-Oleum clear because then you can wipe it down with ethanol. But anyway, any thoughts on stress test? Or just whatever?
So that's a great question. I would say in the spirit of my new attitude towards experimenting, I would say try it till it explodes and then just do it safely, test to failure.
That's my question.
Hi, Jennifer Koblinski from Virginia Commonwealth University in Richmond, Virginia. I'm just curious, I was thinking as you were talking also about like the nose cone, right? So tons of people break those, but also there is a company that is selling like a manifold where it's clearly just 3D printed too, right? You can put 5, and it's not that cheap. So I guess it's like twofold. One is, I don't know, like, do you think that's patented? Or like if you looked at an idea, you could make it and once, maybe it costs that much for you to make it the first time, but then once you printed more? How do you guys deal with that if some other company is selling it?
Is this recorded? This is recorded. So I think patent-wise, I mean, if you were to go out and sell copies of it, that would be questionable or illegal. If you reverse engineer it and make one, I mean, you designed it to some extent. I guess you could go and research what their patent is and see if you're infringing on it. But generally, I think if you design something and print it, you're
Yeah, and
allowed
there
to
might
use
not
it.
even be a patent, right? So I
Right.
guess that's the other question.
Yeah, I think if something is out in the real world and you design something that looks like it, I don't think that's against the rules particularly. Do you know something about this?
Yeah,
I know a lot
Okay.
about this, actually.
Okay, yeah, please.
As someone whose boss said, if you don't get sued every couple of years, you're not working hard enough. No, patent is, by the way, a civil suit. You're not actually going to jail over it, and they can only assess damages on if you were selling it or whatever. So I'm not telling you to do things, I'm just saying the damages have to be worth it to them to come after you, and if you're reproducing $10 or $100 things, they're not gonna find a lawyer in the world that wants that case. Just FYI.
Well, I guess I'll also add that I've purchased things and they come in the box and they're 3D printed, and I'm like, why, what? I should have just done this myself. So I do more and more myself now.
It makes me think of that, I guess that Napster argument. I think all of us are old enough for that. Like, you wouldn't download a car, you know, it's like a but I don't care, whatever. Tim Chai, University of Delaware. Thinking about the rapid prototyping, you can make a bunch of iterations, right? And so now you have the one thing that you know works. What's the recycling of all of those other things? Do companies take those things and mash them up and turn them back into PLA, or do they just go into the ocean to end up in the fish?
PLA is a compostable plastic,
Nice.
just so you know. You know what compostable means, though? It needs to go to an industrial composting facility. You can't throw it out in the woods and nothing will happen.
Gotcha.
It's hard because I love sustainability, but from my observation, none of it gets recycled.
Okay.
What I find the most annoying is the spools that it comes on also are not recyclable. So you're throwing away spools, plastic, and we throw away lots of plastic powder. Like, it's sort of wasteful at this point, but I think that's part of prototyping also, is you're experimenting, and that's
Sure.
part of it. I can see in a manufacturing setting, you could tune your process to really waste less, but unfortunately, I think there tends to be a lot of waste, unless there's someone who seems to know better.
I know there's a homebrew that is for people to take PET bottles and pre-fill them out.
Gotcha.
You can find one of them on dinners.
Okay.
And there are products now for a couple $1,000s for grinding up your PLA and extruding filament, but PLA is really cheap. It would be a lot of PLA to get
Yeah.
to $1,000.
And then you have like color issues. I
Yeah.
mean,
And
I've seen that one, and I'm like,
junky, you know.
why would I pay $1,000 for mixed up brownish filament?
Hi, I'm Seth, University of Massachusetts, Amherst. I was hoping you could opine just a little bit further on the cost-effectiveness argument of 3D printing facilities. Having worked at multiple institutions in their core facilities, I've seen a broad range of applications for 3D printers. I think when I was at Penn State College of Medicine, it started with an engineer just bringing in their 3D printer to address a discontinued part in their MRI facility, and over COVID, it just expanded into all kinds of applications. And so we developed a 3D printing core around all of that because there was so much demand. But after a while, leadership came and started to ask us the question of, you know, how cost effective is this really? And I think I saw a couple of examples. There was a C-clip that I think you had designed to lock a cage door, and you mentioned it was like 5 cents worth of plastic. But the real cost is much more than 5 cents because there's a lot of labor that goes into it. So it could be hundreds of dollars for that. And then I think, Dave, you also mentioned, you know, you could maybe tie wire around it, and it's not quite as reproducible, but it still kind of keeps the door closed. So can you kind of go a little bit further in the cost effectiveness arguments that you could maybe propose to leadership when they kind of are assessing the total cost of the core facility?
Yeah, so like that C-clamp, when we sold it to the investigator, and even before that, additionally, when I had purchased the printer, I had to do a full proposal with ROI, and basically I created a rate setting that was based off of, you know, I have this machine for a couple $1,000s, I have a useful life of 5 years, and how much can I print over that time? It's so cheap that it's like it takes 5 cents an hour to print, or do you do per gram?
It depends on the printer, but sometimes.
Yeah. And then, so then you just charge the investigator for your time. I throw like an initial setup fee, which covers my time of just uploading it to the computer and then sending it to the printer. and then charge them for the amount of filament used, and then the duration that the printer ran for. So if it ran for 1 hour, that's 1 hour off its useful life for $5. So they end up getting that part for $12.
Hi, I'm James from University of Arizona. I just wanted to say I was so impressed with the Amherst kind of partnership, graduate student to undergraduate. It sounds like an incredibly rewarding experience for the undergraduate to be able to put their skills, which they're developing in their program, into use. And obviously for the graduate student, this is an incredible resource for them to have kind of their own little pet wizard who figures it out. My question was, is there any kind of professional certification that could be attached to this? Or, I mean, obviously it's, people are getting a mechanical engineering degree, but if there was a, I just wanted to know if there was anything along those lines currently or maybe in the future, kind of an emphasis on 3D print and rapid prototyping practices.
Is your question for, could the engineers get certified or the graduate biology students?
Probably the engineers, but
I haven't seen a lot of specific like 3D printing rapid prototyping certifications out there. Certainly in the CAD world, engineers can get certified as a certified SolidWorks developer, professional, or things like that. So you can demonstrate a proficiency at specific softwares. But no, I haven't seen any. This is not even a skill that we teach that much in the engineering field. So it's not clear where anyone gets these skills, I mean, including myself. It's more kind of from experience. And actually the students I find who are good at this are ones that have been usually tinkering their whole life. Frequently it's with automobiles, and sadly that's kind of been in decline the last couple decades, kids working on cars. But yeah, it's sort of a homegrown skill that I'm trying to teach to more kids, I think, as we go.
Thank you.
How can I tell if an STL file I find online is going to work or if it's going to stink?
I can answer it too. But.
Print it out.
That's one way.
As much as possible. So for those of us that, they circle around in our core communities and it's like, hey, I just made this, tube holder that'll fit on the machine. Like, I would love to just take that and print it, but not go through all the hundreds of iterations. That's the point where it's not going to be worth it. Are there just any quick signs or tells that this isn't going to work or that this is going to require a lot more time?
So it depends on the software you have. Some software can analyze STL files. So to get in the weeds just a little bit, STL is a file type that's specific to 3D printing that is a three-dimensional file type. It doesn't have error checking for whatever reason, so it can exist and be totally wrong. We have $10,000 software that can look at it and find the errors and fix them sometimes, but if you don't have that, there are some free options that can actually tell you whether it's watertight ahead of time, and that means everything is closed, like it's watertight. Hope it's self-explanatory. That's the only thing aside from printing, unless more ideas from the audience.
Google SketchUp has some plugins. There's like an object logic check. There are two different plugins that you can do that will show you that there are gaps or faces inverted, stuff like that on STLs. You need a plugin also, but it's all free to import STLs into Google SketchUp, and sometimes it can take a day and a half.
Nice.
So what's really great, particularly about FDM or extrusion-based printing is it's exploded in the consumer space, which means that there's lots of users on the internet and lots of people posting solutions to things. So like Nick was saying, there's lots of stuff on YouTube. If you Google your problem, there's lots of solutions. If I take one of these $1 million printers and I Google the problem, no one has posted any solutions because there's 100 of them in the world and they're all in businesses where you're not making YouTube about how you fixed it. So it's it can be very easy, it can be easier to use the internet to help troubleshoot those kind of problems.
Then second question is okay, is there a resource for folks like you, like the 3D core directors, that are trying to meet the other 3D core directors to kind of tackle those? We have a new one that just kind of started. I know that they're kind of reaching some pinch points where they would love to be able just to talk to other people running these kind of cores.
Andrew, are you gonna make that happen? So feel free to reach out to me. I would be happy to be in that group. I've done some regional get-togethers with other similar core facilities do 3D printing. If you're into 3D printing, the conference to go to is next week in Chicago, the Additive Manufacturers User Group, which I will be at, but you need to be serious about 3D printing to go to that one.
You think there's enough like mass within ABRF to have like a 3D printing working group?
This is the third 3D printing session I've seen in 9 years, and this is the most well-attended. And I think we're going towards, again, tracking the beyond the bio capabilities. I think there's definitely a play for materials cores to be here. So it might start, more broad, but I'm a huge advocate of getting everybody we can here. So if you have 3D printing folks in your schools and you think they would benefit from being here, or rather, we know they'd benefit from being here, so we just need a cohort, right? And what we can start with, and Dave, and Nick, I can set you up with it. Here's the ABRF hat and Kool-Aid drinking that I'll share with all you. There's an online community. So it's not even about just getting here once a year. There's an online forum where we could create a 3D printing or materials chat. And the way I've seen them work in the admin and other fields is just people posting questions, how do I do this? So a lot of willing people who have a lot of good ideas are willing to share. We just got to get them connected.
Cool. Thanks.
Hi, John. I'm part of the large University of Arizona contingent. I have one quick question that might just be stupid, and one that's more of a tips and tricks. For the short question, is there a point at which metal 3D printing is undercut by objects that don't require, the fancy structures you can print, or you could just rapid prototype and send it off to your university's CNC shop or commercial CNC? And my other question was if either of you could speak a little bit to like decontamination practices and plastics and how those would interact, either UV decontamination or ethanol, things of that nature.
Can I take the first one? So the first one was a question about metal 3D printing. Yeah, metal 3D printing is difficult and expensive. It has a long ways to go still, I think. It's certainly not as easy as extruding plastic. For most people, I get a lot of requests where it's a part designed for CNC that they want a metal 3D print, which is generally a disaster. I will say with metal 3D printing, you need to design for metal 3D printing from the beginning. And unless you need it to be 3D printed, I think you're better off going with CNC. Because to be fair, that process has been around for a long time. It's been optimized. You can get it anywhere. It's cheap. And you get a nice result. To be fair, metal 3D printing's only been around for 20 or 30 years. It's still developing. It can do a lot of really interesting things, but it's still a pretty niche area at this point. So your second question was sterilization, right?
Practical experience with labs needing to decontaminate the plastic things you print for them. Like you spoke to, how porous the material can be. You can solve that with PETG. But I'm curious about UV exposure and alcohol, things like that. And if you have
Yeah, so UV is just going to penetrate and always destroy pretty much everything. At that point, exposure, just reprint another one. But with the porous objects like the PETG stuff that I have, it does have a high point or a high melting point, so it just can go through the autoclave.
Yeah, our nylon 11 also has a melting point of like 180 C or something. We boil it in dye, actually even color sometimes, so it autoclaves okay.
My question is pretty simple. Can I have one of those dragons, please? I recently got my own 3D printer, and I was tired of my 9-year-old daughter asking for one of these articulated dragons every time we went to a game and hobby store. And I was like, well, why don't we just buy a factory instead? And so we went with a Bamboo Labs. It's been a pretty good purchase. It's been active almost nonstop since we got it. My friend basically said, if you want the 3D printer to be your hobby, go with something else. If you want 3D printing to be your hobby, go with Bamboo Labs. And so it's been pretty easy. One thing that I've noticed though is that initial layer that's printed down seems to be absolutely critical. And sometimes you just don't get a very good, start and everything fails. So what are some tips and tricks to just make sure that you are set up and ready to go so you can walk away and come back with a toy or whatever else in the end?
So the most common ones, is your specs right on the machine? Is your bed hot enough to hold it? The simplest one is to just get a glue stick and then just put a layer, thin layer of glue on it.
Glue, okay.
And that will usually always hold that base layer.
Okay.
Are you not using glue stick now?
I am not. I will wash with isopropanol in between prints, but no, never put on a glue stick down there. And an actual adhesive, never.
Yeah, so there's, so adhesion to the bed is very important.
Yeah.
One thing I've learned is, your layers are about 100 microns, say 100 to 250 microns. And if your bed isn't flat everywhere to 100 to 250 microns, then you could be not touching the bed and jamming into the bed on different parts of the bed, which is why newer printers actually measure the bed and create a map of the bed for the first layer.
The Bamboo Lab ones does.
They do. So we have some that don't, and that becomes a disaster very quickly. But on the glue stick front, a tip that I've learned is you can take the glue stick and do it, but it'll be like lumpy because it's a glue stick. If you take a wet paper towel and you put the glue stick down, but then you rub the glue stick until it all becomes a liquid, and then you just kind of wipe, and you almost wipe it off, but leave a super thin layer of gluey glue stick, it works really well.
Okay.
There are also other products on the market for bed adhesion that you can buy. Some people also like unscented hairspray. Aquanet, literally from the 80s.
Yeah.
Like, it's the same chemical as the glue stick, but you can spray it on.
Okay. Thank you.
Yeah, and then another thing, kind of like the reverse of it, if you see your object and it's adhered onto the plate, they call it elephant foot. If the bottom of your print is supposed to look like this, and you have a slope like this, that means your bed's too hot.
Too hot?
Yeah.
Okay. All right, I appreciate it. And my daughter does too.
Thank you for your talks. I'm Scott Newkirk from UNC. I honestly never thought that I would come to the ABRF and be even close to being an expert in anything. So the first thing I wanted to say was for all the people that had questions about waste and all that other stuff, the first thing would be to actually talk to somebody that knows how to do it or has done it before. That will save you a lot of time, effort, and waste. The second thing was for you, I was wondering, did you have to drive traffic to people to use your 3D printing facility? And how did you do that?
Yes. So build it and they will come, I think is always a joke, right? Because they don't actually come. And we've had to drive traffic both on campus and externally. So the traffic on campus has been mostly word of mouth. That's been all of our traffic creation. That's not true. Okay, you were there. So Andrew drove a lot of traffic. He was my boss at UMass for a long time. And I think it's just trying to get the word out as much as possible. I do have an anecdote where I went to like a neuroscience meeting and I talked for 5 minutes at the end. And all of a sudden, after the talk, like 10 people wanted to line up and talk to me. And I had no idea that this many people had 3D printing ideas that they wanted to work on. But I guess you have to get out there and present what you do. In the region, I would just go to events, usually like manufacturing events for local businesses. And as much as 3D printing is exciting and in the news, et cetera, and big companies are doing it, there are tons of small companies who have no idea what it is and could benefit a lot. Maybe that's being in a more rural area like Amherst, but I think just trying to find a place we can overlap with them and sort of share the concept has been really helpful. And I think a lot of them, once they see the value, then talk to each other. And we've had good organic growth like that.
Thank you.
Hi, my name's Jennifer Gardner from the Stowers Institute in Kansas City. And I do confess to being also dragon motivated. But this is a real question. I'm not a 3D printing expert. We do have one on site. And we have these adapters that we frequently use. I operate large liquid handling robots. And a lot of our 3D printed adapters for plates, like Petri dishes and things, we need to pop things in and out a lot. And the ones we have are really tight, and you kind of have to like wrench them out, and they don't really seem to be getting any better. Would you recommend a different type of material, or like a different design that has like tiny teeth that could kind of, we just need more play in these adapters than we currently have. So I don't know if that's like a materials problem or a design problem.
Do you have the original design file? You just have an STL?
I don't personally, but I know who has it.
I mean, there's a quick fix, which you could print it 1.01 times larger. It would make the whole thing 1% bigger. And then,
it does need to be tight initially.
oh, it needs to be tight and then be loose.
Yeah, so it's good that it's tight, but it's just to get it out and in and out like multiple times.
So now you want sort of a spring. So with plastics, you can do what are called flexures a lot of times. You can put features in that flex.
Okay.
So usually you make the plastic very thin in one location, and it can actually bend safely for a lot of times, I guess.
Okay.
That's a little bit more complicated design. There are many ways design-wise to solve it, I think. We can discuss afterwards if you want.
Okay, thank you.
Hi, I'm Annalisa, part of this gang over here. My question was, Matt and I, we discuss 3D printing sometimes, but what kind of supports are your favorite when you're printing something that kind of has an overhang, and what's the cleanest snap?
Do you have an opinion?
Be really good with an X-Acto knife. It's my favorite tool once it comes out. And then depending on your thickness, sometimes I just get away without supports. So just drop it down to a smaller layer. And then, even if you do that route, you may get it may look a little funky, but sandpaper, finish it right off.
I'll say my favorite supports are no supports. I mean, if you have control over the design, if you can design without supports, like way better. When you print in metal, the supports are also made of metal and they're welded to the part, so you have a lot of incentive to not use supports. There is also an adjustment. You can adjust the height between the support and the part itself, and getting that just right gets it to pop off versus be adhered versus be useless. So kind of dialing that in.
Hi, I'm Kay. I'm from the University of Rochester. My question, I guess, is kind of naive, but I'm from a facility where we want to use a 3D printer, but we want someone else to do it. But we're in a situation where we need like a specific material that's from a high-end type of printer, right? But when universities talk about this, they talk about going in at the low end at first. And is there any disadvantage to jumping into the big kids pool, or is it something that you would kind of iterate and we should just use that sort of more basic system? Because we need chemical resistance, and so we need like the nylon printed ones or whatever. I don't know all the details.
Which printer is it you're considering?
I'm not considering anything.
Oh, okay.
I'm considering begging someone who knows more about it, but it's just that we need the nylon 11 or 12, that you can't just do the easy printing with. You have to have like the whole thing because it has to be DBE resistant.
So this feels like
Thank you.
This feels like a softball question in the sense that my answer is you should come to a core facility and we could do it for you.
Well, yeah, you did mention that kind of in passing at the end, that you do take external things. That was my that was another question that I had too, because we send it out, but these little companies appear and disappear, and it's like every time we need to print something, we have to find a new company to start over because that little company didn't make it, or this company takes 3 weeks, or there's like so much variety or variability in what you get to, and like we have to print extras because they're not going to work. So yes, now I'll just send it to you.
So feel free to reach out. We can print it for you.
Definitely will.
I mean, we have like a Mark Forge printer that prints the same stuff as the Prusa, but costs $10,000 instead of $2,000.
Right.
It's onyx, which is a very nice nylon plus carbon fiber blend. And if you were to buy something like that, yeah, it really depends. If jumping in, I think, depends more on the technology you're getting rather than the price point.
Okay.
I would say that extrusion, FDM, pretty easy to work with. You start to work with resin, you start to work with powder, you start to work with metal powder. Those are much trickier. You get into like facilities issues, like safety things.
Right.
Anything that extrudes, it's generally safe except for ABS, which needs to be ventilated. But
Okay.
yeah,
Thank you.
certainly feel free to reach out. Happy to talk more. I
Okay.
love talking about new printers.
Thank you.
I'm thrilled with the conversation. I'm going to interrupt to say we have about 5 minutes left, but again, after here, there's a couple of technology showcases you should definitely make sure you check out. I want to keep the conversation going. So just want to give people a frame of reference, and if you didn't ask a question you like a dragon, we have plenty. Please, thank you for those who came up and did ask. But please, feel free.
Sorry. My last question is, do you prefer to use like just for FDM printing, do you have one slicer software that you use, or do you become proficient in each printer's somewhat proprietary slicing software?
For me, I use Digilabs. It just works well with Dremel. They have a full library of the most common filaments. So you're able to just select your filament and it will change all the specs. So you don't have to go back and change them all yourself and remember what you had last time.
Prusa comes with their own slicer, which is based on Cura, I think, I like it a lot. We have like 5 different manufacturers of printers, so each one has their own interface. I can't say any is the best. They all have pros and cons. So
It seems like Ultimaker's Fiorella iterates pretty quick.
yeah, I think whatever is comfortable for you. There are lots of choices.
So just from the arena I come from, I'm a microscopist, and there's all these, you can go to these week-long courses and get hands-on on the instrumentation and learn in a compressed, dense environment. Is there some sort of like scientific focused printing workshop that you can get this crash course? And if not, could you guys put one together and then we could go to like printing camp somewhere nice? I've never been to Amherst.
Yeah. I honestly think it's a great tie back to here, right? This would be a great place, and it made me think of something else too. The proliferation of 3D printing. Walking through campus, I can't tell you how many labs don't have 3D printers. It seems it's becoming ubiquitous, right? Everywhere you go, I'll just get this little one to do myself. So I think, right, coming to ABRF, and what we do is try to find ways to make things more efficient, try to reduce the duplication, and make sure what people use is good product versus just waste throughout the campuses. Maybe again, that's a place where ABRF can kind of dual task, right? Say, it's important to have the right people helping you with these things, and not every PI needs one, even if it's only a couple $100. All the other costs that were mentioned add up really quickly. And oh, by the way, like you're going to be training yourself, and that's time that you're spending that could be used towards actual research and projects. So yeah, maybe this is a place where if we build that community, we can offer some real impact right away by saying, don't waste your money on printers, put it towards people who exist and can help you. And here's some training materials for those who are going down the print path. But I like that idea.
Oh, we could have a workshop next year.
Yeah. Are you anybody on the PC next year?
I am.
There we go. And there are clearly a lot of folks doing it, right? So we can start that community and find you some folks to host that. I'm going to steal a question, not because I want to drag it, because I think we have 1 minute left, but just because I thought we'd have a lot of dead time. I'm grateful we didn't. But I guess one's really quick and one's maybe a little bit longer. How many of the things that you make, specifically, I think you, Nick, maybe not so much, Dave, are just because people broke things in their lab?
A majority, yeah.
And the second one is just because it's fun, and these, I've always been in love of all of the toys, but what's some of the more creative and more, maybe, what are some of the weirder requests you've had to print? Or maybe, what's your favorite print? What's your favorite print? We'll go that way.
Do you know my weird story? You have a lot of stories.
I think mine was the fish feeder I made. I went to ALAS, which is the governing body for lab animal science, and just several vendors came up to me really interested about it, and it was kind of more so I'm more interested to go to the open source route for that.
Still thinking?
There's so many, yeah, I don't have one right now.
Stump the chump. The two favorite that I can remember you did, so you mentioned the giveaways. So you made Pokemon. We had was like 40 printers in the library that were all student, go use whenever you want. But just to show the quality difference between what these professional printers look like, they've had just a batch of little Pokemon and they always disappeared, so they must have been fun. But the fish, is that allowed to, that's published, right? The fish project that you did?
I can talk about that one. So we have a multi-material printer. It can do, it's a Connex object, so it can print out rigid material and flexible material kind of within the same print. So imagine prototyping a toothbrush with a grippy handle or a razor, whatever those consumer products are. So what they wanted was a fish fin, but it had bones inside that were rigid, but then fin material is more flexible. They were using it in a tank to actually flip the fin and simulate a fish motion and measure the force that created. So they needed something that was both flexible and rigid at the same time. So that was kind of a fun one. The other fun one, you said the library. We had a customer who needed like, I don't know, 100 pieces of something by 3 days from now. And I was like, okay, I don't have that many printers, but the library has like 40 maker bots. So I called the library, and the library is like printing all weekend. I'm printing all weekend. We somehow make all these parts and deliver them, but we utilize every printer available on campus to sort of get this project done.
Which is a plug to say, make sure you know where your printers are, because I'm sure there's a lot more of them than you realize. All right, we're at time. Again, I'm sure the folks would love to keep chatting, and you guys will be here at least through today.
Please come get these. I don't want to take them home.
Let's thank our presenters and thank you all for participating.